Hey guys, here again to do another problem with you. This is number 4 from the very last problem from the packet I gave you this week. So in this one we got a rocket. It fires from rest with an upward acceleration of 6 meters per second squared for 11 seconds. After this time, the engine shut off. The rocket freely falls back to the surface of the Earth. It tells us that g is going to be 10 meters per second squared. We can use 10, not 9.8. Part A wants us to draw a graph of the velocity of the rocket as a function of time from t equals 0 to the time the rocket strikes the ground. Now, unfortunately, can't really do that on this one because I made the numbers too big, so we're not going to have room in this graph to draw it till it strikes the ground. So we'll just draw as much of the graph as we can, and that's fine. You can do the same thing. So I've already drawn part of it here. So we started at 0, right, our velocity time graph. Started at 0 velocity, and I'm accelerating at 6 meters per second squared. So that means that every 1 second I'm gaining 6 velocity, from 6 to 12, 18, 24. I can't really tell where 6 is and 12, so I'm just going to go to 60 over 10. That's the same thing, that's 6. So put a circle there. And then 1 more second to 11, so I go to 66, right about there, and I draw my line. From this point, the rocket then will fall down, back to the Earth. So as soon as the rocket stops firing, gravity kind of reasserts itself and starts pulling the rocket down with an acceleration of negative 10. So from here, I go down 10 over 1, 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 down 10 over 1. So somewhere in there. This is an estimate. Try to be as precise as you can, but it's hard to tell where 56 and 46 is. So just do the best you can. I'll draw a straight line. Straight as I can manage, and then something like that. Alright, so that's our graphs. So we're going to skip this part. I may have mentioned that in class. I hate these motion maps. They're kind of annoying. So leave that alone. Alright, so here's our graph. This is what it should look like. Accelerating, accelerating, accelerating with the rockets firing. Rockets are firing. Rockets stop firing. Slow down, slow down, slow down, slow down, slow down, slow down. And then here. Now a lot of students think that from this point, where my pencil is, that this is when we start to fall back towards the Earth, but that is not correct. As you'll see in a minute, the point where we actually start to fall back to the Earth is actually down here. This whole time, our velocity is a positive value. Even though the graph is going down, we are slowing down. Our velocities are getting smaller, but they're still positive, which means my direction of motion is still up towards outer space. All right. So let's look at part B then. Determine the height of the rocket when the engine's shut off. All right, for this one, let's list our givens. All right, we're always going to do the guess method. What are we given? Well, we know that our initial velocity was 0 because it's a rocket and the rocket started from rest. We know that our acceleration as the rocket goes up when the engines are on is 6. Let's see, what else do we know? We know that we know it lasts for 11 seconds. So our t is 11. And we know our initial position is x naught is 0 because we're starting on the ground. We call the ground 0. And what's our unknown? What are we trying to find? We're trying to find how high we go. Our height, that's our final position up in the air. How high do we get? X. All right, so with this information, looks like we're going to need which equation? X equals 1/2 at squared plus v naught t plus x naught. That's the equation we're going to want to use because it has everything listed. So here we substitute and we solve. So we're just going to plug this stuff in. V naught is 0, so that's nice. This goes away. X naught is 0. This just kind of goes away. We're left with just this. So we have x equals 1/2. A was 6. T was 11. That's squared. Don't forget to square it. And I just punch it in my calculator. Okay, I found my calculator. So we just plug it in. And we're going to have, let's see, 11 squared times 6 times 1/2. 363. That is our final position up in the air. X is 363 meters. And there we go. That's how high we get first 11 seconds. All right, let's go to part C. C says, determine the maximum height that the rocket reaches. Now, a lot of students make this mistake. They think that this is the maximum height the rocket reaches, so they just write the same number over here. But that is wrong. Remember back at our graph, this is when this spot here where my pencil is where the rocket's engine stops firing. But it does not instantly, suddenly start to drop, right? When I throw the ball up in the air in class, the moment the ball leaves my hand is analogous to when the rocket shut off. The ball is no longer in my hand. I'm no longer applying a force to the ball, but it still goes up because it takes a few seconds for gravity to slow it down and then turn it around and make it fall back, right? So even though the rockets aren't firing here, it still has upward velocity. Here it's at positive 50, and then at positive 40, 30, 20, 10, and then this much longer, that's when it stops going up and then it starts to come back down. So for part C, we got to figure out, there's actually a few ways to do this problem. I'm going to do the long way first and then show you a little shortcut. Determine the maximum height the rocket reaches. Well, we already know it went up in the first 11 seconds, 363 meters in the first 11 seconds. That's basically to here, right? Now, what we need to do is figure out, okay, how much higher does it go, right? Well, we know a few things. We know that we're already going, let me start to that again. We already know that we accelerated for 6 meters a second squared for 11 seconds, and we started at initial velocity 0. So how fast are we going? That's question number one. How fast are we actually going when the rocket shut off? Right? Now you kind of tell from the graph, right? It's somewhere in between 60 and 70, but we'll do the equation just to be sure. So with these these values here, these are givens, my unknown. My equation I'm going to use is V equals AT plus V naught. I'll plug everything in. A is 6, T was 11, that was 0. V is going to be 66. Okay, so I'm going 66 meters per second. So if I'm going 66 meters a second when the rocket's shut off, how long does it take for gravity then to slow me down enough to where I stop? Right? How long does that take? Well, again, this time I'm going to kind of reset here. All right, I'm going to reset. Actually, I'm going to get a fresh sheet of paper because this part of the problem is a little bit longer than the others. So I'll leave that on the screen like that. I'll start below it here. Okay, here we go. All right. So what we're trying to do is find out how long it takes for gravity to slow the rocket back down to 0 velocity. Remember we said in class today, on Thursday, that an object that's going up, at its highest point, its velocity is 0, right? So now the rockets have shut off, it's in free fall. Our initial velocity is now 66, because that's how fast it was going when the rocket shut off. We want our final velocity to be 0, right? Because that's at 0 is our highest point. We know our acceleration is now negative 10, because now gravity's taken over, and rocket's being pulled down at negative 10 meters per second squared. And what we want to find out is time. How long does that take? How long does it take for gravity to slow this thing down? So we're going to use our givens and our unknown. The equation we're going to use again is VAT plus V naught. We'll plug in our numbers here. It's 66, T, negative 10, and then equals 0. So I'll just do my algebra. I subtract 66 from both sides. Negative 66 equals negative 10 times T. Divide by negative 10, divide by negative 10. T equals 6.6. All right, so now we know that it's going to take 6.6 seconds for gravity to slow our rocket down. So how much higher do we get in those 6.6 seconds? We already know we're 363 meters off the ground when the rockets are firing, but we kept going up, right? We kept moving up for a little bit, for 6.6 more seconds until we actually stopped. So how far do we get in those 6.6 seconds? Well, we're going to use one more equation. Now we know what our T is, so now we go back to the old trusty 1/2 AT squared plus V naught T plus X naught. Now, our starting position is 363. because we're already that high in the air, right? We're already that high. This is when a rocket stopped firing. So we're going to add that. We're going to make that our starting position. 363 for our x naught. Our time, now we know our time is 6.6 seconds. Right? We're trying to figure out how much higher do we go in that 6.6 seconds. Our v naught is 66 because we're already going that fast, right? So that's 66. Our time again, t squared, that's going to be 6.6 squared. I'm kind of writing backward, it's kind of weird, but that's all right. A is negative 10. Half of that. Let's squeeze this in here. Draw a line to separate this out. Half of that, and then we have equal. All right, so we have x equals 1/2 a. Oops, I tried to put the negative sign on the wrong side of the 10. That's silly. 1/2 negative 10. That's my acceleration of gravity. Times 6.6 squared is my time. Plus, forgot my plus sign. Plus v naught times t plus x naught, my initial position. All right. All right. So we just plug in our numbers and solve. And once we do all that, let's see. 0.5 times negative 10 is, of course, negative 5 times 6.6 squared is 43.56 times negative 5 is negative. Let's just simplify this down a little bit here. I'm going to skip a little bit around. Hopefully you're good with the algebra. It'll be negative 217.8. That's this part plus 66 times 6.6. That's 435.6 plus 363. Now, so I'm just simplifying down, right? I just multiply this part together and this part, and then add that. All this equals x. So now x equals, just add this up. So we have negative, what's the negative sign on this calculator? I can't find it. Oh, there it is. Negative 17.8 plus 435.6 plus 263, and we get 580.8, and that is how high we go. Now, that's the long, dirty way. Let me show you a better way with the graph. All right. Earlier we said that we found out that it took 6.6 seconds. Where was it? Oh, over here. 6.6 seconds for gravity to slow a rocket down to 0, right? So we know, go back to our graph, from this point here, at 11 seconds, it took 6.6 seconds to slow the rocket down to 0, which means we know that the whole time the rocket was going up, had positive upward velocity, was 11 plus 6.6 seconds. So the total time it took for the rocket to go up was 11 plus 6.6 seconds, which is 17.6. Now we have been saying in class over and over again that the area under the curve of a velocity time graph is displacement, right? Now if I only consider the positive velocity, then if I find the area under the curve of the positive velocity part of the graph, I'm going to find my positive displacement. In other words, the upward displacement into the air. So let's do that real quick and see if we get the same answer as over here. Guess what? We will, because that's how physics works. It works. It's awesome. Okay. All right, so let's see. It's a triangle, right? Triangle, so we're going to use 1/2 base times height. So our base now is 17.6. That's how long we're in the air for. So 1/2 base is 17.6 times the height. Now our max height was 66, right? That was how fast we got the rocket going when the rockets are firing. The height of our triangle, 56. So we do the math. 17.6 times 66 times 1/2, 580.8. The same number we got with all those long and arduous calculations, right? So this is what I mean when I say the graphs are awesome. Learn how to use the graphs. It still saves you time. All right? I spent 6 minutes doing all this garbage. I could have just done this in, a minute or less. All right, so we found our displacement. our maximum height, 580.8 meters. Determine the amount of time the rocket is in the air. This part is we're basically almost done. We've already found out the rocket goes up with the rockets on for 11 seconds, and then goes up a little bit further for 6.6 more seconds. So the rocket's going up for 17.6 seconds, right? So now we just got to figure out, okay, well, how long does it take to fall back down, right? Well, we're going to use x equals 1/2 at squared plus v naught t plus x naught. All right, now this time, let's see what our values are. We already know our maximum height was 580.8. So that's our starting position, right? We're 580.8 meters up in the air. So x naught is 580.8. X is 0, right? That's our final position. That's the ground, right? That's where we're going to end up. A will be -10. V naught is 0. Remember, we're only calculating. This is the path of the rocket. We've already calculated all of that stuff. We've calculated that already. We're done with that. We've done it. We're going to kind of make a new problem. We're going to start over, and we're going to start right here and find out how long it takes to go just down to here. So we're kind of ignoring all of this. We're going to just kind of pretend like it doesn't exist just for a minute. So our starting velocity is just what it was at the very highest point, which we said in class is, of course, 0. So v naught is 0, v naught 0, x is 0, x naught is 580.8, and a is -10. And then what's t? How long does it fall for, right? So we'll plug our numbers in and we'll solve. So we have 0. I'm going to draw a little line here just to make this. All right, so we have 0 equals 1/2 times -10 times t squared plus v naught is 0, right? So 0 times t is 0, so that's plus 0. X naught, however, 580.8. All right, subtract this over to this side. So we have -580.8 equals -1/2 times 10 is 5, so -5 times t squared. Then I'm going to divide by -5. Divide by -5 both sides. -580.8 divided by -5 is 116.16. 116.16 equals t squared. Don't forget the squared. And then, of course, how do we get rid of squared signs? We square root both sides. Then I get t. I square root this number. Square root that guy. And I get about 10.78, or you can round up to one decimal place. 10.8 is perfectly fine. 10.8 seconds. Then I take that number and I add it to the 17.6 that I was going up for, right? Going up for 17.6 and then down for 10.8. So my total time then, 10.8 plus 17.6 is 28.4. 28.4 seconds is my answer. And there you go. And like I said, you can skip E. We'll talk about motion graphs, but these are just kind of annoying right now. They're not that big a deal. So there you go. Hopefully that helps some of y'all understand the graph a little more. If we could have continued the graph, of course, it would have gone down to the negative region, right? And eventually, it would have just kept going like this. And eventually, when the rocket hits the ground, the negative displacement, all this, would have equaled the positive displacement, right? But unfortunately, I didn't make the graph big enough for you. That's my fault. But hopefully you understand these steps. And if not, please let me know. We can talk about it in class. And that's that. Have a great day, guys. I will see you tomorrow.